In Chapter 3, we're going to be looking at numeric representations of data, and in 3.1, we're going to be focusing on central tendencies. So that's going to be the mean, median, and mode. We're going to start with mean. That's often referred to as the arithmetic mean, and what you probably commonly know as average. So if you've ever taken an average before, you have actually calculated a mean already. What we know for average is we're supposed to add up all the values and divide by how many there are. For our example, let's refer to page 118 in your book, example number 1. These 10 values represent test scores, and we're going to assume that these 10 values represent an entire population. So we've got a really, really small class of 10 students, and here are their 10 test scores. So for the mean, there are actually two different symbols that we use to represent mean, depending on whether we're talking about a population or a sample. So since these values represent an entire population, we're going to use the symbol mu. That's a Greek letter. Typically for population information, we talk in terms of Greek letters like mu, sigma, rho, those kinds of things. And then when we're talking about sample information, we'll start using Roman letters. So we'll have X's and S's and R's, things like that. So the mean for a population is defined to be sigma x over capital N. What we're supposed to do is we're supposed to add up all the values and divide by how many there are. So in math, capital sigma means summation, or add everything up. X is the variable, so add up all the variable values, divide by, this is our population size, how many values there are in this entire population. So for our example here, what we're doing is we're going to add up the 82 plus the 77 plus the 90 plus the 71 and on, making sure we take every single value in the population and add it up. Then what I do is I take that entire sum and I divide by how many values there are, and the population size here is 10. There's 10 test scores. So I'm going to whip out my calculator here. I want to add up all these numbers. So I'm taking 82 plus 77 plus 90 plus 71 plus 62 plus 68 plus 74 plus 84 plus 94 and plus 88, and I get a sum of 790. And so I'm going to take that sum and divide it by 10, which gives me an average or a mean of 79. So this is, again, the average or the arithmetic mean of an entire population. Now, normally populations are huge, and we don't have much information about populations to be able to compute stuff like this. So what we tend to do in real life is we take a smaller sample and we find information about that sample. So let's try and scale this down a little bit, and instead of finding the mean for the entire population, let's find the mean of just a small sample of these values. So just for the sake of the example, I'm going to pick 4 random scores from here. I'm going to use my calculator to do it. So I'm going to go, I'm going to pick numbers between 1 and 10, assuming this is number 1, number 2, number 3, and so on. And I'm going to pick 4 values, and my calculator is giving me number 8, which would be this guy, number 6, which is this guy, number 4, and number 3. So you can get that using technology, you can get that using a random number table or whatever. We're just using it for the sake of the example. I'm trying to find now a sample mean, and let's just use these 4 values that I've underlined as my sample values. And so the mean of a sample is not mu, but now is called x bar. So I use those Roman letters, or like English letters, such as x, to represent sample information. So x bar. It's found the same way, but when you see the formula, instead of dividing by capital N, you're going to divide by lowercase n, because lowercase n is a sample size. Capital N was the population size. But still, the idea is we're adding everything up, dividing by how many there are. So when I go to add up these values, I'm not going to add everything, I'm only going to add the values in my sample. So I'm going to take the 90 plus the 71 plus the 68 plus the 84 and divide by how many there are in this sample, which is just 4. All right, so that's 90 plus 71 plus 68 plus 84 gives me 313. And again, I need to divide that sum by the sample size, which is 4. And that gives me 78.25. So that's different than our average for the entire population, and that's fine. The idea is that the population was 10 values, and the sample was only 4 of them. And so the population and sample were different groups of test scores. And so I would expect the averages for those different groups to be different themselves. It's just the nature of samples being different from populations. But that's how we find means in general. We take all the numbers, add them up, divide by how many there are. If it's a population, we use that Greek letter mu. If it's a sample, we use X with a bar over it. So now let's move on and talk about the next measure of central tendency, which is called the median. For the median, it's the same symbol regardless of whether you're doing a population or a sample. We use a capital M to stand for median. And what we're supposed to do is we're supposed to put these numbers in ascending order and basically count our way towards the middle. And whatever the value is that's right in the middle, that's going to be our median. So what I need to do in this example is I need to rewrite these 10 values in ascending order. So I look and find the smallest value, which looks like 62. So I'll put him first. And then I'm just going to make a little mark so I know who I have got. Next comes 68. Next would be 71. And then next is 74. And then 77. And then it looks like 82. And then 84. And then 88, and then 90, and the biggest one we've got is 94. So again, putting them in order from smallest to largest, and then what we want to do is we want to start at each extreme end and kind of count our way towards the middle. Now, if you have an odd number of values, as you count towards the middle, you'll find exactly one value in the middle, and that will be your median. But in this case, we have an even number of values. So as I count towards the middle, there's not going to be just one single value in the middle there. There's actually 2. And so here's what we have to do. For the median, we find those 2 values that are in the middle, and we find their mean or their average or what's exactly in between them. So for the median here, what we're going to do, I guess I'll do it down here. For the median, we're going to take the 77 and the 82, which were both in the middle, and find their average, meaning we're going to add them up and divide by 2. So 77 plus the 82, that should give us 159. And when I divide that by 2 or cut it in half, that should give me 79.5. So that's the value that would be, in theory, right in the middle here. And the idea is that this number, that 79.5, divides or cuts my data into halves, where half or 50% of the values are below that number, and half or 50% of the values are above that number. So it's the middle point. All right, so now let's see what happens when I start changing some values around. So let's see. I want to see my original set, and I'm going to start changing some things and see what happens. Just so I don't forget, I'm going to write down my original mu and my original m. So my original mean was 79 for the population, and my original median was 79.5. And I just want to see how this stuff changes when I'm going to change a value here. Here's what I'd like to do. Let's pretend that my smallest value was not 62, but let's say it got changed to 0. So instead of 62, I now have a 0. I want to see how that affects my average mean, and I want to see how that affects my median. So for the average, or the mu, again, we're supposed to add everything up and divide by how many there are. So let's try this again. We're taking 82 plus 77 plus 90 plus 71. And instead of 62, I'm now adding 0 just to say what happens if it changes. Plus 68 plus 74 plus 84 plus 94 plus 88. There's still 10 values, so we're still dividing by 10. So let's see what happens here. So we've got 82, 77, 90, 71, 0, 68, 74, 84, 94, and 88. That gives me a sum of 728, which I need to divide by 10. So that gives me an average of 72.8. And I want to compare that to what it used to be when that 0 was actually a 62. It used to be an average of 79, and now it's dropped significantly to 72.8. So what we can note here is that when I have an extremely low number, when I've changed the number from a 62 all the way down to a 0, I've changed it to what I would consider an outlier. It's so drastically different, so much drastically lower than it used to be. What that does to my mean is it makes it lower. So I'll just make a note here that drastically decreasing a value will drag down the mean. It will drag down the mean. It makes that mean smaller than it used to be. So decreasing a number, making a drastically smaller number, making an outlier that goes that away, pulls the mean down. It makes it smaller. So now let's see what happens when we talk about the median and how it changes with this obscurely low value that we've added in. So let's see what happens. We know again with the median what we have to do is put it in ascending order. So now the smallest value isn't a 62, but it's a 0. Next comes that 68, and then the 71, 74, 77, 82, 84, 88, 90, and 94. Did I get them? 1, 2, 3, 4, 5, 6. Good, I got them all. Okay, so again, the idea of the median is that you put them in order and then you try and find the middle number. Again, we've got those two numbers in the middle. What you should notice if you compare this to last time is those are the same two numbers that are in the middle. So when I find the median, I'm still looking at the number that would technically be in between 77 and 82. So again, that's taking 159, dividing it by 2, and I still get 79.5. That's what I had before. So adding on an extremely low value pulled down the mean and made the mean smaller, but it didn't affect the median. The median is still in the middle. So medians are unaffected by really low numbers. And if I did the same thing, but with a really high number instead of a really low number, it would pull the mean up, but leave the median alone. So since that median doesn't change with really low or really high numbers, since it's not affected by those outliers, we say that the median is resistant. It is resistant to outliers. Small outliers don't make it smaller. Big outliers don't make it bigger. The mean, however, is not resistant. It gets persuaded by those really small or really large numbers. It gets pulled down or pulled up. So the median is resistant. The mean, however, is not. And so that also has to do, or it also affects the shape of the distribution. So if I have a distribution that is, say, skewed left. Remember when we talk about which direction it's skewed, the direction is where the tail is. So this is skewed left. And the idea is that most of the information's over here on the right, but there must be some weird outliers that are way down to the left that are really, really low that are kind of pulling some of that curve down there. And when they're pulling that distribution down, what they pull with it is the mean. And so when I compare the mean with the median is still going to be kind of near the bulk of the information. It's in the middle, but the mean will have pulled down. If I look at a distribution that's skewed right, again, remember the direction of the skew is where the tail is. So if we're skewed right, the tail's over here. And again, the idea is most of the information, most of the data is here, but there's some weird obscure values on the right that's pulling that tail over there. It's pulling some of the distribution. And with it, it pulls the mean, mu. The median kind of stays in the middle where it was, but the mean gets pulled. It gets influenced by those high outliers. So small outliers, low outliers, pull the mean away from the median, pull it to the left. Big or high outliers pull the mean to the right of the median. Now, if you have a symmetric curve, the idea is that the median is always in the middle, but the mean will also be in the middle if you don't have weird outliers on either side pulling it one way or another. It just kind of stays in the middle. So if you have a symmetric graph, the idea is that your mean and median are basically the same. They're not always exactly the same, but they're going to be really close. So if your mean is left or smaller than your median, you have a skewed left. If your mean is to the right or is larger than your median, you're skewed right. If they're about the same, you're symmetric. All right, so now let's look at our third and final type of central tendency, and that's going to be the mode. And the mode is not something we calculate, it has to do with counting. What you're looking for is something that is the most popular or the most frequent value. Now, I'm going to go back to my original. This 0 was a for instance, but it originally said 62. Originally it said 62. So if I look back at my original set of 10 test scores, the idea behind the mode again is I want the most frequently listed number. And if you look at these, there's really no number that happens more often than any other. They all happen just once. And so for this particular example, I'd say there is no mode. There is no one number that is more popular or more frequently listed than any other number. Sometimes, though, we can have a mode, something that is more popular than another. So let's do another for instance. Let's say that this 84 wasn't an 84. Let's say it was an 82. So let's pretend that's an 82. And now I've got an 82 here and another 82. It happens twice. No other number happens twice. They all otherwise happen just once. So 82, if it happens more often than everything else, I'll say that 82 is the mode. Now it is possible to have no mode, like we saw, if nobody happens, more often than anyone else. And it's possible to have one mode where one number happened more often than everyone else, but it's also possible to have more than one mode. So here's an example of how that might look. Let's again just change another number. Let's say the 62. I keep picking on that one. Let's say he was a 68. And now I can see there are two 68s, there are two 82s, everything else just happens once. So there are now two values that are more frequent than all the others. They happened to be equally as frequent as each other. So it's 82 and 68, they both happened twice, so they're just as popular as each other, but they're still more popular than everything else. And so it just means we had two modes. You have 68, which happens twice, And you have 82, which also happens twice. Nothing else happens that often, just those two. So they're both the mode, and since there's two of them, we would call it bimodal, two modes. It's possible to have multiple modes as well. So if you had, if this 77 was in fact a 71, now I've got 71 as another mode because I have several things happening more than once. But if I had everything happening twice, then we're back to the situation where there's no one that's more popular than another, so there's no mode. So if everyone happens the same amount of time, no mode. If there's one that happens more often than anything else, one mode. If there's two that happens more than anything else and they're the same popularity, two modes. It's possible to have 3 or 4, but that just doesn't happen very often. All right, so in terms of looking at all these different kinds of measures of central tendency, we may want to know when should we use each one. So let's talk about the mode first. The mode is probably the one you'll use the least often because there's not a whole lot to it. It's not mathy, so we don't like it so much. The mode is what I want you to use if you have qualitative data. With qualitative data, there's no numbers that you're dealing with names or labels or categories, and with those kinds of names or labels, we can count how many times a label occurs, and so it makes sense to talk about which one happens most often, which one's most frequent. And so qualitative data can talk about mode. Qualitative data, though, cannot deal with median or mean, so this is the only way we can deal with qualitative. All right, let's talk then about mean. Let's talk about the mean. Mean can deal with quantitative data, but what we saw with the mean is that the mean gets influenced by really low values or by really high values. Those outliers pull the mean one way or another, and it's not resistant to that. And so I don't really want to deal with the mean if I have those outliers affecting them or influencing them. So I'm going to say only deal with the mean if you have a symmetric distribution. Otherwise, outliers are influencing that mean and it's making it so it's not really representative of the big picture. So only if the distribution's symmetric should we talk about mean. And then in terms of median, again, this is quantitative. But as we saw, the median is resistant to outliers. So when you have really low or really high values, that median doesn't feel any desire to move one way or another. It just kind of stays put in the middle. It's resistant to those outliers. And so the median is a great tool to use if we happen to have a skewed distribution. So if it's skewed left or skewed right, then let's use the median to be kind of our go-to representation of the average of a particular distribution.